This lesson is about the resistance of a metal wire or a conductor. This picture illustrates a metal wire with length and cross-sectional area. And the question is this: how do a cross-sectional area, the length, and the type of metal affects its resistance? Let me start with length. As the length of the wire increases, then the resistance also increases. As the cross-sectional area increases, then the resistance decreases. To understand the relationship between area and resistance, you can imagine this wire like a tunnel where electrons need to pass through. So wider the tunnel, so electrons have more space to pass through, less resistance. As the tunnel gets thinner, smaller, so now the electrons, they have a smaller space to pass through, therefore will have more resistance. The third factor is related to the type of material. So as the number of free electrons in a particular type of conductor increases, then the resistance also increases, because now I have more electrons confined in this material. Example of metal wires material are copper, silver, gold, and nichrome. In conclusion, we can say that the resistance is proportional to the length. We can also say the resistance is inversely proportional to the cross-sectional area, because the area increases, resistance decreases. And the resistance is proportional to the type of material that we are going to represent with rho. Combine all these three variables together, we can state the resistance of a wire is equal to the product of resistivity with length over area, cross-sectional area. So combine all those factors together, the resistance of a wire formula is equal to resistivity, the product of resistivity with length over cross-sectional area. So rho is the resistivity in ohms meter. So this is the unit. L is for length, and the unit is in meter. And A is the cross-sectional area in square meter. In this section, I'm going to sketch a graph of voltage in terms of length of a wire. Here is the explanation about this diagram. So this thick line here represents the wire, any wire. So I'm going to place this wire over a ruler so I can control the length. Then I'm going to supply to this wire a voltage, let's say hypothetically 12 volts. So this one is going to be constant. Constant 12 volts. Now, I'm going to use the terminals of this battery. One I'm going to place at the beginning of this wire, and the second one I'm going to move on different sections of this wire. Now, as I move on different sections as this wire increasingly getting longer, I'm going to read the voltage on that particular section. So I have one terminal of my voltmeter here, and I'm going to start with right here. So if I'm going to read just a small, very small section of this wire, almost zero, I should be reading pretty much the entire voltage supply, because there is no voltage drop in a small section, because the resistance here is very, very small. Resistance is proportional to length. If my length is very small, the resistance is also very small and will not consume too much voltage. So my voltage here is going to be reading pretty much the entire value of this battery supply. For this reason, I'm going to mark on this Y portion of this graph 12 volts. And for the length will be about 0. Now I'm moving the terminal of this battery supply to another section of this wire, and I need to adjust the voltmeter to this new length right here. And now I'm going to read a new value. So here on this graph is my new segment. Now because I have more wire here, so I have more resistance, which means that the voltage here is not going to be exactly 12, will be less, because some of this voltage will be necessary to provide the energy for this section right here. So my voltage is going to drop, it will be less than 12. Now in this step, I'm going to increase the length of this section that I want to read, and I'm going to adjust my voltmeter for this section right here. So which means that now my 12 volt supplies is going to drop even more, because now I have more resistance up to this section. So the voltage across this segment will be even less as the prior reading. So I'm going to draw my graph as long as my voltage drop a little bit more, because the length now is longer. So here should be a good point. Now I will move the terminal of my battery a little bit longer and stop right here. So my voltmeter reading should be less value than before, because now I have more resistance here. So the value has decreased as my length is getting longer, because now I have more resistance, and that should be the value right here. Now the terminal of the voltage supply is right here at the end of this wire. So now all the energy is being delivered, and there is nothing reading on this section, because the resistance on this is maximum. So in this case, so now the voltage is 0 and the length has on its maximum value. Now connecting all these dots, I should have a straight line like this. A couple of notes about this graph. So I know this is representing length, but in this case we have to look length as a portion of resistance. So as the length is getting longer, the resistance is getting higher. So for each segment, I'm calling here R1, R2, R3, and R4 to represent the segment for each section. So R represents the resistance of this wire. So R is proportional to length. So as length gets larger, then the resistance of the wire also gets larger. An important note as a follow-up of this statement, as the resistance of the wire gets larger, then the voltage on the wire drops more. In this example, I sketch a voltage over length of a uniform wire. So the wire is the same throughout. The question is, how would be a voltage length graph for a non-uniform metal wire? Like, for example, this shape where the length, the cross-section, you have two sections. One cross-sectional area is greater than the other one. It's like that we have two separate uniform wire right here. And in this case, we have three different cross-sectional area, kind decreasing. And this one is kind cone shape. So how we would draw a voltage length for every single one of those three examples. So for the simplicity of this drawing, I'm going to focus just on the wire and the voltage supply. The terminals of the voltage supply is going to be connected in one end of this wire, and the other one will be on different sections of this wire as long as the length is increasing. So because here we have two distinguished area, we are gonna call this one 1 and this one 2. Because we have two defined cross-sectional area, this one is greater than this one, and we know that the relationship between resistance and cross-sectional area is inversely proportional. So if this is smaller, my R is bigger, is larger than this one, which is smaller. Again, longer the wire, greater than resistance. I'm going to sketch this graph with a different approach that I did on the prior one with the uniform wire, because I have two sections here with the same length but different cross-sectional area. I'm just going to, on the length, on the x-axis, define both sections right here. So this is for the first one, and this is for the second one. This thin line represents a graph for a uniform metal. So I'm going to draw over this graph for a non-uniform. Now on this graph, I have here the length for the section 1, and this the length for the section 2. A side note that would help to solve this problem is that steeper the line means R is larger. So I know that my R, my resistance, is larger on section 2 and smaller on section 1. So how do I translate this into a line, a graph line? Let me try this way. If I establish a point right here, and I'm going to draw a line making sure this one is steeper, I can do this to start with, draw a line over here, and then a second line over here, and compare those two lines. So this one here is steeper. And that way I can represent graphically how the voltage over length graph is translated into this type of non-uniform wire. So comparing the those lines. So this here is steeper than this one, which represents how the resistance of this wire is going to change with the cross-sectional area. Then you may be thinking, what resistance got to do with length? Because this statement from the prior graph is that resistance is proportional to length. So as length gets larger, then the resistance of the wire also gets larger. This way, we can easily sketch a voltage length graph based on this information. Our second case of non-uniform metal wire, we have now 3 sections, each section with same length but different cross-sectional area. We are going to supply the voltage for this wire of 12 volts. Like I said, as an example, could be any voltage. One terminal will be fixed, and the other one we are going to be moving around and to determine the resistance per length segments. Now that we have 3 sections, I'm going to identify 1, 2, and 3 sections right here, and then I'm going to compare the resistance for each section. The segment 3 of this wire is the smallest one, the small cross-sectional area, so that will be my larger R, followed by this one, and then a very little one here in comparison. So now I'm going to represent on the length 3 equal segments with the resistance, in this case, R1, R2, and R3. I want to make a correction here, not a correction, just following the same pattern. So let me call this here R1 and this R2, just like I did. I think it's a good idea. So here I'm representing those 3 sections for each segment of this wire, and this thin line represents how the graph is for a uniform wire. So remember, steeper the line means R is larger. So in this case, my steeper one will be this. So you can use those lines to guide you. So right here, I'm gonna do this. It will be steep enough. So like this. So that will be, okay, so my second option is, let's say this one. And my third one will be even less. So now we have 3 segments. I can actually make a little bit lighter. This one, it was too much. Let's trace it. Okay. So now we have this one here is the steeper one, because here this one is the big R. This is the small R. And this is kind in the middle. Okay, now we have a wire with like a cone shape. So for each section, you have a different cross-sectional area. I'm going to supply voltage for this wire of 12 volts. And let's see what happens. So for each section, we have here different area. So R, or the resistance, changes gradually. And I don't have a defined section like I did on those prior one for a non-uniform wire. So I'm going to go ahead and pick kind of 4 sections, 1, 2, 3, and 4. Now if I'm going to compare the resistance for each one of these sections, I know the resistance in this section here is smaller, and this one here will be big. So that's how it's going to change the resistance. It's going to increase with the decrease of cross-sectional area. So to sketch this graph, I'm going to get 4 sections here from this gradual change on cross-sectional area. And this fine line represents the uniform wire as a reference. Okay, so to finalize this graph, all that I need to do is have in mind that as the length of the wire gets longer, the resistance is getting longer and the voltage on the wire is dropping. So here are the points that we can select and draw a curve like this. Now, because it's a curve, we are going to check the resistance relate to a line be steeper compared with the other ones. Is you just place your ruler on this point and draw a line, draw another line. So as you see, it's getting, the line here, the tangent line is getting steeper. So as a side note, is steeper, the tangent line you do when you have a curve is equal to a larger resistance. This problem from October 11, paper 14, question 33, is related to the voltage distance graph for a non-uniform wire. So let me read for you. A conductor consists of 3 wires connected in series. The wires are all made of the same metal, but have different cross-sectional areas. There is a current I in the conductor. Point Y on the conductor is at 0 potential. Which graph best shows the variation of potential with distance along the conductor? First, let me write here as a side note, same material, means same resistivity and same current. So which means that the only variable that is changing is the cross-sectional area. Here we have 3 sections with the same length. So I'm going to connect each section to the corresponding section of this graph, all 3 graphs right here. So here the resistance is inversely proportional to the cross-sectional area, which means that this one, let me start with the narrow one, has the highest resistance, and this the lowest resistance, and this something between. The best way to solve this problem is comparing the steep of lines. Steeper the line, R is greater. One observation, for each segment, if I cover just the rest, segment 2 and 3, and show just one, this is kind a uniform wire. So the uniform wire, we know that as the length gets longer, so the resistance also gets longer, and the voltage across this wire would drop. So there is a uniform drop of the voltage on this section as the length is getting longer. With this being said, I can eliminate the option C and the option D because it's not showing a gradual drop in the voltage as the wire gets longer. It's not showing that. So those two will not translate how the voltage drop behave on a wire as the wire gets longer. Now we have just options A and B. Now, what we say here is the steeper the line, R is greater. So R is greater right here on 3. So when we compare, let's work with option A. When you compare the steepness of this line with this and with this one here is steeper compared with the other two, and this one represents a high resistance, and this is a low resistance, which is showing promising my A option. Let's see what B options is showing. Okay, B option, let's compare the steepness of this line. So this one is the steeper. Compare with this one, for example, is less steeper. So this here is showing that the R here is greater and R here is smaller, which is not what's going on here. So my option for this question is option A. One more question related to the voltage length of a non-uniform wire is this one from May-June 2013, paper 13, question 32. The circular cross-sectional area of a metal wire varies along its length. There is a current in the wire. The narrow end of the wire is a reference potential of 0. And which graph best represents the variation with distance along the wire of the potential difference V relative to the reference 0? Translating here the part of the potential difference, which means that how the potential difference or the voltage is dropping as the length of this wire is getting longer. A couple of points for each section of this wire right here. For each section, the cross-sectional area is gradually decreasing, which means that the resistance of this wire as the cross-sectional area is getting smaller, so the resistance is getting bigger. So I'm just comparing here both ends. So this end here, the resistance is way greater than this end right here. Now, because length and cross-sectional area are two variables that are changing here, so this is not on a graph that will be just a direct relationship. So we'll have resistance is proportional to length and inversely proportional to the cross-sectional area. So let's eliminate a couple of options. Option A is showing a suddenly drop of the voltage with the length of this wire, which is not correct. So this is eliminated. B, this is a graph if this wire would be like uniform wire. For uniform wire, so that will be the behavior of the graph, the voltage over length. So this is not a uniform, so it's also eliminated. Then you have option C, which is a curve. So in order to determine if this curve represents how the voltage drop with the length, so let's select 2 points on this line and draw a tangent over this line and compare both. So this one here is steeper than this, which means that the resistance is greater than this section right here. And on this one, I'm going to do the same thing. I'm going to select 2 points of this graph and draw a tangent line. Tangent line right here and the other one right here. So this is kind of opposite. This is steeper than this. So looks like that the resistance here is greater and this one is smaller, which is not representing our situation here. So the correct option is C.